Welcome to the Off-Grid Power Systems Information Series. I am Russ Fling, engineering consultant for Off-Grid. I'm glad you are joining us. We are a Victron distributor and a distributor of the best of other manufacturers. Off-Grid provides system design and integration services as well as sales of products. We specialize in off-grid solutions, whether it is an RV or a remote cabin for personal or business use. I'll be discussing bus bars today, a deceptively simple device, but critical for a system using lost current. We'll concentrate on placement does matter, not just size. This is a theoretical discussion. Actual currents shown in this video will depend on variations on the system, and an engineer should properly design the system. The size of the bus bar needed is determined by the current, orientation, bus bar material, the temperature rise you're willing to accept, whether it's in free air or enclosed, and even the surface characteristics. You can find online many references. Most specify a vertically oriented bare copper bus bar and a 30 C rise in temperature in free air. This is a great place to start, but we will not discuss the actual design of a bus bar in this tutorial. Sizing the bus bar, as in wires, should be based on the fuses, not the devices, since the devices could supply or source more current than expected in a failure mode. Since all the components, including wires and connections, will have some variations, a safety factor should be included. We'll show you that placement of the sources and loads does have an impact on the size of a bus bar you need. Rigorous electrical circuit analysis not given, just the results. Shown here is a typical configuration of a Victron system with a Lynx power in on the left and a Lynx distributor on the right. A Lynx shunt or BMS could be between them. If we consider just the first Quattro requiring 4 amps of load, each battery supplies 133 amps. Note, we are only showing the positive bus bars for clarity. The negative bus bar currents will be similar, just the opposite polarity. If we add the second Quattro's load, each battery supplies 267 amps, and the bus has a maximum current of 800 amps. The third and final Quattro, each battery supplies 400 amps. If we add the MPPs, which are not supplying any current, the situation doesn't change. The bus bar has a maximum current of 1200 amps, and this is above the 1000 amp maximum spec for Lynx products. However, at Off-Grid, we don't recommend more than 500 amps continuous on the Lynx products. The size of the Lynx bus bar should only be able to carry 720 amps continuously, with a 30 degree temperature rise in free air. It is not in free air, and there are few vents, and that's why we recommend 500 amps. It can carry 1000 amps for short periods of times, but not continuously. Overheating can lead to serious issues in this or any other part of your system. Now let's consider a different placement of the loads and sources of current. Same devices as before, and let's see what happens if we place them in different places. The Quattros have the same loads as before. The batteries supply the same currents as before. Starting from the left, the Quattro is supplied by the leftmost battery. The middle Quattro is supplied by the middle battery, and the right Quattro is supplied by the right battery. The MPPs are supplying no current, and this doesn't change any of the currents. Surprise! The maximum current on the bus is 400 amps, just by connecting the devices in different positions. Thus, the bus bar can be smaller, saving copper, and since the max current is less, there's less loss of power in the bus bar, and thus more efficient. Note, there is not one place on this bus bar to measure the total battery current. This is not compatible with current Victron BMS systems relying on an external current shunt, but some battery manufacturers can work with Victron BMSs without a current shunt. What will happen if the MPPs are supplying current? We'll start with the Quattros requiring load currents. When the batteries supply 267 amps each, later we'll show that the MPP's currents will make up the deficit. The left Quattro is supplied by the left battery, the middle Quattro is supplied by the middle battery, the right Quattro is supplied by the right battery, but the Quattros still don't have enough current to supply them. Here come the MPPs to save the day. Each supplies 200 amps, which provides the remaining current. The maximum current in the two places in the bus bar combined to 400 amps. The middle part of the bus bar is less than 400 amps, although the currents combine at each connection point to 400 amps. What happens if the batteries are imbalanced? Or if there are differences in the connections to the bus bar? By the way, we recommend that identical wires in length and size are used to connect the batteries, and similarly, Quattros and MPPs to minimize imbalances. Again, we start with all Quattros requiring 400 amps. Now the batteries are extremely imbalanced. The left Quattro is supplied from the left battery, but current is left over. The middle Quattro is supplied by the left battery and the middle battery, but again, current is left over. The right Quattro is supplied by the middle battery and the right battery. The MPPs are not supplying current, and this would only improve the situation if they were. Again, the maximum current in the bus bar is 400 amps. So what happens if one of the batteries fails? Again, we start with all Quattros requiring 400 amps. Now only two of the batteries are providing current, 600 amps each. This is a precarious situation since they are at their max, and the system would completely fail if the fuse on one of the remaining batteries fails. The left Quattro is supplied as follows. The middle Quattro is supplied by the left battery and the middle battery. The right Quattro is supplied by the middle battery and the right battery. The MPPs are not supplying current, and they again would only improve the situation. Again, the maximum current in the bus bar is 400 amps. As you can see, the placement of loads and sources can make a big difference in the size of the bus bar required in a system. Careful selection and placement of the devices on the bus bar can reduce the size required for the bus bar. However, it does have implications in the selection of equipment. For instance, requiring batteries that work with a BMS without an external shunt. In smaller systems, this isn't an issue, but for larger systems, the design of the bus bar and how it is connected becomes a critical design issue. Using an oversized bus bar will lead to smaller voltage drops in the bus bar, and consequently less power is consumed in heat. These losses may be small, but who wants to throw away energy? As in wire sizing, the length of the bus bar is also a factor. All things to consider when selecting and designing your bus bar and how to hook it up. Similar to the beer commercial, placement saves copper, more efficient, lower losses, works great. I hope this tutorial was helpful and useful.